Welcome back, Apologia 3rd edition, week 6, day 1, pages 108 to 113. But really, we will be covering 110 to 113 because we will do the lab in class. During the discussion of Rutherford's model of the atom, we mentioned that it was inconsistent with electromagnetic theory. Nevertheless, since that model seemed to be the only way to explain Rutherford's experimental data, it became the accepted model of the day. As chemists sought to understand more about atomic structure, they did more experiments. One of the experiments that shed some light on atomic structure involved adding energy to atoms by heating them or passing electricity through them. When this was done, the atoms emitted light, some of which was in the visible spectrum. The interesting thing was that each type of atom seemed to emit its own unique color, or colors of visible light. For example, when mercury atoms were heated, a pale blue glow would occur. On the other hand, when electricity was passed through neon atoms, a bright pink light was emitted. As chemists investigated these experiments further, the mystery deepened. They learned that the colors which were being emitted during these experiments were the result of a handful of individual wavelengths of visible light being emitted by the atom. For example, when electricity is passed through hydrogen gas, the atoms emit a purple light. This light is composed of exactly 4 wavelengths: violet, 410 nanometers, indigo, 434 nanometers, blue, 486 nanometers, and red-orange, 656 nanometers. These wavelengths mix together to form a purple color. What makes these results interesting is the fact that atoms seem to emit individual wavelengths of light. This is very unusual. Most colors that we see are the results of a range of wavelengths, not individual ones. For example, if we were to make a red light, we would probably paint a normal light bulb red. The paint would keep all the wavelengths, except the red ones, from getting through. The light coming from the painted bulb would not be made up of just one individual wavelength. Instead, all the wavelengths from 700 to 650 nanometers would be there. The fact that atoms emit only a handful of individual wavelengths indicates that something unique is at work. Another interesting fact is that each element produces its own unique set of wavelengths when heated or electrified. While hydrogen emits visible light with wavelengths of 410 nanometers, 434 nanometers, and 656 nanometers, tantalum, Ta, emits visible light of only a single wavelength, 535 nanometers. This little fact is quite useful. After all, if you need to determine the atoms in a substance, one way to do it is to heat the substance up and determine the wavelengths of light that are emitted. Since each element in the substance will emit its own unique wavelengths of light, you should be able to match the elements with their respective wavelengths and eventually determine the elemental composition of the substance. This is the main way that astronomers determine the elemental makeup of distant stars. Stars are bright because the substances that make them up are very hot, and they therefore emit light. They emit so many different wavelengths of light that to our eyes, the light appears white. However, a scientific instrument known as a spectrometer can analyze the light and determine all the individual wavelengths that make it up. Then, matching the elements to their expected individual wavelengths can determine the elemental composition of the star. This method of analysis, known as spectroscopy, can be applied to chemicals as easily as it is applied to stars. It is one of the most useful tools a chemist has to analyze unknown substances. The ability of atoms to emit individual wavelengths of light also helped Niels Bohr develop his own model of the atom. Bohr took the planetary model developed by Rutherford and added his own little twist. Rutherford assumed that all of the electrons orbited around the protons in a single orbit. Bohr suggested, instead, that there were several possible orbits that the electrons could be in. Furthermore, he suggested the electrons could jump from one orbit to another. In addition, by the time Bohr had come up with his model of the atom, the neutron had been discovered by Chadwick. Bohr put the neutrons and protons together in the center of the atom and called it the nucleus. This model is what is shown in figure 3.12, the Bohr model of the atom. One very important advance that Bohr made in developing his model was his assumption that the electrons could only jump into and out of specific orbits. So if an electron decided to jump out of orbit 1, it could not go just anywhere. It had to jump into another allowed orbit, such as orbit 2. And even though it could be in orbit 1 and jump to orbit 2, it could not be anywhere in between. This type of assumption is called a quantum assumption, and at the time it was considered rather odd. After all, if the electron could go to either orbit, why couldn't it go somewhere in between? Bohr had no answers to this question. Indeed, even modern chemists have only a rough answer, but it was a necessary assumption in his model. One of the first questions you might ask is this: how do the electrons jump from one orbit to another? The orbits that are farther away from the nucleus require more energy. If an electron wants to jump from an orbit close to the nucleus, orbit 1, to an orbit far away from the nucleus, orbit 3, it can do so by absorbing some energy. This is what happens when you heat a substance or pass electricity through it. When an electron moves from an orbit close to the nucleus to an orbit farther away from the nucleus, we say that the electron has been excited. So if it starts here and it goes to this one, we say it has been excited. If, on the other hand, an electron would like to move from an orbit far away from the nucleus to an orbit close to the nucleus, the electron must somehow get rid of its extra energy. In other words, while in the orbit far from the nucleus, the electron has more energy than it would in an orbit close to the nucleus. So the guys out here have more energy than the guys here. To get to that closer orbit, the electron must find a way to get rid of that excess energy. It does this by emitting light. When an electron moves from an orbit far from the nucleus to an orbit close to the nucleus, so when it goes from here to here, we say it has de-excited. When you heat a substance and its atoms emit light, you are witnessing a two-step process. Electrons in the atoms first gain energy because of the heat and move into orbits that are far away from the nucleus. Then, after they sit in the far orbits for a short time, they decide they would rather be back in their original orbit. So they emit light to get rid of this excess energy and go back to the original orbit. This is what makes the flames of a fire. When wood is burned, the chemicals in the wood are first changed into carbon dioxide gas and water vapor via a combustion reaction, as we have discussed before. However, heat is also produced in the reaction. This heat excites the electrons in the gases surrounding the fire, and they move to orbits farther away from their nucleus. However, after being there for a while, they decide to de-excite back to their original orbit. To do this, they must emit light. This is where the pleasant yellow-orange glow of the flames come from. If you light a natural gas oven, you will notice that the flames are blue and not orange. This is because the natural gas company intentionally contaminates its natural gas with a substance whose atoms emit a blue glow when excited. The difference in the flame color is due to the fact that different atoms are being excited. You can examine another similar phenomenon if you burn wrapping paper. The dyes in most wrapping papers contain elements that are different from other papers. So, while most papers burn with the same yellow-orange glow that wood burns with, wrapping paper typically burns with green, blue, or red flames, because of the element that makes up the dyes in it. Do you remember that Bohr assumed that an atom's electrons could only be in certain orbits? Since each orbit has a specific energy associated with it, this means that an electron can only have certain energies. If it is in orbit 1, it has a certain energy, E1. If it is in orbit 2, it has another higher energy, E2. But since the electron can never be in between orbit 1 and orbit 2, it can never have any of the energies between E1 and E2. This assumption makes no sense at all, because common sense tells us that any object should be able to attain any energy at once, provided there is some way of transferring the necessary energy. Bohr said there were only certain energies that the electrons in the atom could have. This, another quantum assumption in Bohr's model, is the one we now see as critical to understanding atomic structure. Bohr did not just dream up his model for the atom. In fact, for the hydrogen atom, he had detailed mathematical descriptions of the electron moving in its various orbits. He could use his mathematics to determine the energy of each electron orbit. He could determine how much energy the electron needed to jump from one orbit to another. Once he knew the energy necessary for the electron to jump from one orbit to the next, he could then determine the wavelength of light that the electrons must emit to de-excite. He found that the wavelengths he calculated were exactly equal to the wavelengths that chemists observed for de-exciting hydrogen atoms. This indicated that Bohr was on the right track, and his model for the atom quickly gained acceptance. In fact, even though today's accepted model of the atom is slightly different from Bohr's model, the detailed mathematics that he developed are still taught in college chemistry today. These mathematics, which are a bit too detailed to tackle in this course, provide good insight into the physical mechanisms that hold the atom together. If you end up taking advanced chemistry, you will learn the mathematics of the Bohr model of the atom. Additionally, the stylized pictures of atoms you often see are based on the Bohr model of the atom. Although science has moved past Bohr's model, the scientific community recognizes his achievements to this day.